So we're going to continue learning about different types of reactions, and today we're going to move on to the decomposition reaction. So we want to learn what this reaction is about and how to figure out exactly what we're going to make from it. So in the decomposition reaction, it's pretty much as it sounds. You're going to have a reactant decompose or break down into two or more different products. Now we're going to take a look at three different scenarios here. We're going to look at the decomposition of a binary compound, which is a compound made out of two elements, the decomposition of a ternary compound, which will contain a polyatomic group, and the decomposition of very specific acids. So a binary compound, as we've mentioned, is a compound that contains two elements. In its decomposition, this compound is going to decompose into those two elements. So we're just going to basically split up this one compound into two or more things. So if we examine the decomposition of this example, manganese oxide, well, the two elements that are making up magnesium oxide are magnesium and oxygen. So the decomposition of this is really simple. We're just going to list out the standard state of these two elements, which, magnesium standard state exists as one atom, but oxygen being diatomic would exist as two. And that's kind of all there is to it. If we look at another example, let's say the decomposition of water. So if we decompose water, well, the two elements that make up water are hydrogen and oxygen. And then, of course, these are both diatomic elements, so we should have to show that, they should carry a subscript of 2. And that's all there is to the decomposition of the binary compound. You are just dividing it into the two elements that compose it. The one thing you do want to be careful of, though, which is a really common mistake that people kind of fall into, is that you have to treat the subscripts from the compound independently from the subscripts of the products. Now, it's really common to assume here that the products would be H2 plus O, because you're just looking at H2O and you're just splitting up into the two individual elements. When we do this decomposition, the products are going to be in their standard state, meaning how they are found in nature. And in nature, hydrogen and oxygen exist as diatomic elements. Going back to our first example, okay, we have the magnesium oxide. Again, standard state. So when this decomposes into the two individual elements, we're just going to list out the elements by themselves. You never transfer over the subscripts. And it's a really common mistake, especially when you start learning this stuff, to try to keep them the same. And that's just kind of something that you want to avoid. So it's best to keep in mind that the subscripts never travel from one thing to another. Everything is independent. So now let's take a look at the other type of compound, the ternary compound. In this, we're going to have a polyatomic group, and we're going to focus mainly on three different types of decomposition reactions. So we're going to look at the decomposition of a metal carbonate. So a compound that's got some kind of metal and the carbonate CO3 polyatomic group. So CO3 with a -2. Metal carbonates, like in the example calcium carbonate, which everybody typically knows as limestone, is going to decompose into the metal oxide version and carbon dioxide gas. So if we just take a look at this example, calcium carbonate will decompose into calcium oxide plus CO2. So the decomposition of a metal carbonate will always produce carbon dioxide along with the metal oxide form. And you can see that it's already balanced because it's just the release of the CO2 gas. In the metal hydroxide reaction, you're going to have a metal with the hydroxide polyatomic group, that OH. This is going to decompose into, once again, the metal oxide, and it's also going to form water. So it's very similar to the first one that we covered, except instead of the carbonate polyatomic group, we're going to be having the hydroxide group, and instead of carbon dioxide, we're making water. the products don't really change. So for each of these specific types of reactions, you're gonna more or less make the same iteration of products. And then lastly, taking a look at the metal chlorate, these are going to decompose into the metal chloride version plus oxygen gas. So chlorate is the ClO3 with a -1 charge polyatomic group. And these are going to decompose into the chloride. Okay, a little bit different. There's no oxygen in the chloride, and oxygen gas. And like I mentioned before, each of the reactions are going to more or less make the same products every time, again, with just a different iteration of the metals depending on which metal you have initially. But the metal carbonate decomposition will always form CO2, metal hydroxide will always form water, and the metal chlorate will always form oxygen. And then it's just up to the metal itself to determine what type of oxide or chloride is going to be formed. Lastly, if we are focusing on the decomposition of acids, we only want to see two of these right now. So the first one is the decomposition of carbonic acid, H2CO3. So this decomposes into CO2 and water, always. So these are known products of this decomposition. Same thing with sulfuric acid, H2SO4. This is always going to decompose into SO3 and water. So these decompositions will always make the same exact product. There is no change, no different version of it. That's just what they decompose into.